Section 15.3, double integrals in polar coordinates. You should have plenty of experience with polar coordinates. Any good pre-calculus class would allow for some time in polar coordinates, trigonometry courses, and as well as any good course, any thorough course in Calc 1 and Calc 2 should have you revisit polar coordinates here and there. We're going to go ahead and do this again. Now, I'll do a quick little review of polar coordinates, but you'll find that polar coordinates are a very useful way of integrating double integrals. And many times you'll find that integrating using double integrals with polar coordinates actually make your work a lot easier as opposed to rectangular or Cartesian coordinates. Now, often enough, there are many times where you can do this, where you can actually integrate using rectangular form, but polar seems to be superior in some areas. Now, there are times, though, where polar is much more complicated and actually rectangular is easier, but it really just depends on the situation. Now, in particular, when you have regions like circles, cardioids, rose curves, etc., then you might want to consider using polar form, because polar form is, in many ways, a much simpler task, and it also helps you to try to verify other methods of actually integrating. You actually can find ways to integrate both with polar form and rectangular form and still get to the same answer, but again, sometimes one way is easier than the other. Let's go and do a little recollection of polar coordinates. Recall that these formulas are polar coordinate conversion formulas. So r squared is equal to x squared plus y squared. X equals to r cosine theta. Y equals to r sine theta. And this is all based off of this photo here, this picture. Pythagorean theorem helps a lot with that. So hopefully I'm not really showing you anything new. What will probably be new are the regions over which we will be integrating. For example, believe it or not, this first type of polar coordinate integral that I'm trying to show you is actually a simple polar coordinate. And the reason why it's simple is because you'll notice that everything about this region is constant. You'll notice that the radius, or I should say radii, from the origin has a distance that starts at A going up to B, and that's pretty consistent because, again, it's going around like a polar coordinate should. And that the angles are going from something constant, from a constant angle of alpha in this case to a constant angle of beta. And if you have a situation like this where you have some sort of like it's almost like a pizza slice with a bite cut out of it. It's almost like, it's probably the easiest situation possible when it comes to polar coordinates. But occasionally you'll get stuff that are much more difficult, and I'll show you in a second. But this very simple example is called a polar rectangle. Now, more complex limits look something like this, where and maybe you have constant angles that you are integrating, but you have a region that looks something like this. Now, this looks pretty crazy, but you'll notice at least my angles are still constant. They are constant straight lines here. You see that? And as we rotate, we're rotating from, again, theta equals alpha over to theta equals beta. But still, the radius r is still defined between two curves going down to the origin. It just so happens that these two curves happen to be variable for this second region, whereas the last one, they were consistently throughout the entire region. Now, this is going to lead to two types of double integral conversions. Now, what I'm about to show you is straight from the book, and it looks pretty intimidating, but I would actually recommend that you read it carefully. And after I do a few examples, it won't seem so bad. But in order to change to polar coordinates in a double integral, basically what you want to do is you want to go ahead and replace, it's basically like a fancy version of substitution, and you want to replace any x you see with the formula for x, which is r cosine theta. You want to replace any y with the formula for y, which is r sine theta. But you'll notice that dA over here was replaced by not just dr d theta, but by r dr d theta. And I'll explain more specifically what that means in the next slide. And essentially, more specifically, I should say, if f is continuous on a polar region of this form, then we also can use this. This is the complex version of what we've done before. Now again, if you're lucky, you get something like this, where you have a polar rectangle where both the r values, see how the integral here is closer to dr, that means a and b are values of r. If those are constant and the angles are constant, notice how the outermost integral is corresponding with the outermost differential, then this would be a very nice and fairly simple integral for you. However, remember, sometimes you might get a situation where r is variable from its outermost r to its innermost r, whereas the angles are still pretty constant. But I really want to point out this fact. In both these cases, whether it's this simple case or this more complicated case, notice again, dA is being replaced with r dr d theta in both cases. dA, r dr d theta. Now, it doesn't really matter if you say r dr d theta or if you switch the d theta and the dr. You can still say r d theta dr if you wish. It depends on the situation. But I really can't emphasize this enough, so let me go ahead and show you once again. This is an important note. dA must be replaced with r dr d theta. So why don't we go ahead and try an example and see if we understand. We're going to go ahead and set up these but not evaluate. We're going to go ahead and convert this from rectangular coordinates to polar. So for this problem here, it'd be a good idea to sketch a picture. If you can't sketch a picture, it's okay, but sketching a picture really shows the student where we are actually integrating. As you saw in section 15.2, we sketched a lot of figures. In fact, most of the problems that you noticed we solved, we sketched a picture first. So here we sketch a picture. Now I think we all know how to draw a circle. So if we draw two circles, one with radius of 2, one with radius of 5, but we only consider the first quadrant, we get something like this. I think this is pretty easy for us to see. Here's my little quarter circle here, radius 2. Here's my quarter circle here, radius 5. And we're only considering all this region in here to shade. So I'll go ahead and consider this. Now I want to find, now notice that we are looking for not only area, dA, but it also has xy, which means actually this is going to be a volume. Even though it doesn't say volume, this is a volume because xy is hovering over this region here. And we're going to go ahead and integrate this double integral the following way. So if we go ahead and take this integral here over our region, again, our region being between these two quarter circles and in this first quadrant, we end up getting this. Now let's start with the easy stuff first. Before we panic or get into a fuss over how I got to this point, let's start with the easy stuff. First of all, dA. As you saw on the previous few slides here, dA changes into r dr d theta. Again, dA is replaced with r dr d theta. Many students forget to put the r. It is very important you put not only the dr d theta, kind of like dA has usually use dx dy, but also you need the r there. Again, that's based off of chain rule and substitution into polar coordinates. The next easy stuff also is that I'm simply replacing x with r cosine theta and simply replacing y with r sine theta. I don't think that's too hard. So what about these limits? How do these come into play? Well, the innermost differential is dr, which means my innermost limits here should be values of r. Now r, remember in polar coordinates, r is the distance from the origin to the curve itself. So as we can see, r, the lower limit, is closest to this circle of radius 2, which is why I have a lower limit here of 2. And it goes all the way from the origin all the way up to this outer curve of radius 5, which is why my upper limit here is 5. And why are we only going from 0 to pi over 2? Well, as you can see, we are only rotating this region from an angle of 0 down here up to the positive y-axis, which is, we all know from trigonometry class, pi over 2. And again, notice how the angles are on the outermost integral that correspond with the outermost differential. And actually, this would be a pretty easy integral to solve. It's only asking us to set up, but do not evaluate this integral. But if I were to integrate this integral, I would actually do it this way. Notice this is actually a special case where we can actually rewrite. What I mean by that is, well, you'll notice that all this is just a product of r, something explicitly r, and something explicitly theta. So you actually can rewrite it like this if you want. You don't have to. And then obviously this is definitely a very easy integral. Both of these. I mean, this is like, you can do this from calculus 1 methods with substitution, or you can use calculus 2 methods as well. And this is obviously power rule. So very simple. Let's try setting up another one. Now this one's nice because you already have all the limits given here, but it looks a little intimidating because we have the arctangent, which we haven't seen for a little while. But don't be too intimidated. You'll see after I substitute many things in here, you'll see that it actually becomes quite simple. Remember, these are rectangular coordinates, and many times when we convert from rectangular into polar, it becomes a lot easier. Now, the first best course of action, again, if you can, try to draw the region, and the region is basically going to be based on these figures right here. And again, please notice that the differential here, dy, is closer to my integral that goes from 0 to radical 9, quantity 9 minus x squared. So these are y values. So if you set both of these equal to y, you'll notice that this here is the limit from 0 to the circle of radius 3. So it's a circle of radius 3, and this is going to be the top hemisphere. And then dx is going to be the outer limits here, and that goes from -3 to +3. So essentially this region is going to look like this. It's the upper half of the circle. So converting this to polar would be quite simple. In fact, if you recall, y is r sine theta, x is r cosine theta. The r's cancel, I end up with sine theta over cosine theta, which is just simply tangent. And as we all know, the arctangent of tangent, well, that's going to go ahead and turn out really nice. Before I get into that, though, let's see if this makes sense to us. Now, once again, I'm replacing dy dx, which is actually dA. I'm replacing dA with the same thing, r dr d theta. Replacing y over x with tangent theta. But notice that my innermost integral, dr, corresponds to the radii from 0 to 3. And if you notice, this shaded region consists of all the radii from a radius of 0, which is at the origin, out and up to a radius of 3, all along this half circle here. And of course, our angles are going to be starting at the angle theta equals 0, all the way out and around about to theta equals to pi. After simplifying, you see that we end up getting just simply theta times r dr d theta, which obviously we could actually go ahead and solve this. This is a very easy integral to solve, and you can even just split this up, since this is a product of something explicitly theta times a product of something that is explicitly r. Now I'd like to go ahead and evaluate an actual double integral. Now this one is very similar to the last two. In particular, this one's similar to the example we did 2 slides ago. And actually this one here is very similar to the one we did 2 slides ago, where we were between 2 circles, one of radius 2, the other one radius 5. This one's actually the same thing, but the only difference is that we're between 2 circles, one of radius 1 and the outer one of radius 4. And because we're looking at the whole annular region, instead of just talking about the first quadrant, we're actually talking about the entire 360-degree turn from quadrant 1 all the way around to quadrant 4. So having said that, that hopefully makes no surprise then that we end up getting these limits here. Now before I get into the limits, let's go ahead and try to talk about this one without graphing a picture if possible. We'll start with the easy part. The easy part is, if you'll notice that x squared plus y squared here becomes r squared. So that's just our typical polar conversion formula. And dA, you might wonder, well, how come dA became dr d theta? I thought dA was r dr d theta, and it actually is here. You'll notice, though, that I just went ahead and put it in the front. So here's my r. So again, dA is equal to r dr d theta. I just put it in the front because to me this is more visually appealing, especially if you are trying to solve this using just basic calculus 1 with substitution, your basic substitution. Very simple. So hopefully this makes sense, this setup here. And once again, it's the annular region, which is just basically two concentric circles. The inner circle of radius 1, the outer circle of radius 4. That's why I have my radii from 1 to 4. Again, dr is closest to my integral here, so it's going to be my r values here. And again, we're going all the way around the circle from 0 to 360, which is going to be 0 to 2 pi here. So in the section, the problem we had 2 slides ago, we went from 0 to pi over 2 because we stopped in the first quadrant. Here we're going all the way around the entire, all 4 quadrants. Now, using basic substitution from calculus 1, we just simply end up with 1/2 cosine r squared, going from 1 to 4. And if you're wondering where did the 0 to 2 theta integral go, well, again, notice that this is something explicitly r, so we can just go ahead and focus here on this integral, and then go ahead and take the integral of 0 to 2 pi of d theta right away, which is simply just going to be 2 pi. This negative came from the antiderivative here of cosine, and hopefully that's pretty easy to follow, leaving us with this with our answer. And I've said this before, I'll say it again. As long as you are getting a numerically equivalent answer, I'm okay with it. Let's try another one. Here again, I'm going to try to do this without drawing a region. Now, notice it says here cardioid. So, as I'll show you in a moment, it'll be wise of you to understand how to plot a polar function. So, it will be wise for you to learn how to change your graphing calculator into polar form, and then go ahead and try to learn how to graph these. That would help you see things a lot better. But if you're ever doing any kind of polar form, many times what you'll find is that our region is simply going to be, now again, we're looking for to change this into polar coordinates. So obviously let's start with the easy part. The easy part is this inside right here. So the inside here is just going to simply be r squared. Right? But then I take the square root of it, I just simply get r. So this is simply just going to be r when I convert it to polar coordinates. But then I end up back at r squared because of dA again is r dr d theta. So I end up getting r from this radical expression. I get another r from dA, which leaves me with r squared dr d theta. Now we are a region that is bounded by the cardioid, so we're going from 0, the origin, out to the cardioid itself, 1 plus cosine theta. And then again, we're doing a full 360-degree rotation because it's bounded by the entire cardioid. It's not indicated otherwise. But as you'll notice in future problems, you'll see that there are other issues where you actually should sketch the graph to see for sure if you're going around completely from 0 to 2 pi. But typically that's what you're doing in polar coordinate problems. Now this is pretty simple here. This is just simple power rule. So this is going to become 1/3 r cubed. But I'm going to go ahead and not only do 1/3 r cubed, I'm going to go ahead and substitute in my upper limit. This is 1/3 r cubed. I just replaced the r with 1 plus cosine theta, subtracted by 1/3 0 cubed, so we can disregard the lower limit here. Now here, we cannot separate these into two separate integrals because my limit has something that's explicitly in terms of theta. So before I actually continue here, I actually recommend for this particular problem at this point is to go ahead and expand. So write this 3 times and expand it out, or use Pascal's triangle. Pascal's triangle is a very convenient and quick way to expand this very quickly. If I were you, I would Google search Pascal's triangle to remind you what that looks like. Hopefully you've seen it in the past. A really good intermediate algebra class, you'll learn about Pascal's triangle. And then finally, this should be pretty easy for us to integrate piece by piece. This was back in Calculus 2. This is when you learned how to integrate using just trigonometric functions. You should end up with this. So I know I skipped some steps here. So if you can't quite remember how to go from this step to this step, again, please mark the time on the video, send me an email. I will be glad to show you the middle intermediate steps. Before you do that though, before you email me any questions, I would ask you to try to figure it out yourself and try to go back and look at your old Calculus 2 notes to remind yourself of how to do it. But again, like I said, I am more than happy to show you that step. Do another one. Again, let's try not to utilize a picture. Once again, our x squared plus y squared integrand here is going to be simply r squared. No radical here this time. And you'll know, again, dA also has its own factor of r. So this r squared multiplied by the r in dA is going to ultimately become r cubed. And we're bounded by the region, the spirals theta and 2 theta. And we're going all the way around 360 degrees again. So that should look like this, a pretty easy conversion there. Again, x squared plus y squared is my r squared right there. dA has its own r. We're going from theta to 2 theta and going all the way around all 4 quadrants. This becomes, again, a very easy, very basic integral for us now. Power rule, simple power rule. Fundamental theorem of of calculus, part 2. Please pause the video and try to get to that 15 theta to the 4th yourself. Now it's simple power rule, and we end up with this as your answer. Now, before we continue, I actually have an important note. I want to really make sure that you understand this. We already learned this a few sections ago. But an important note to remember is that there are ways to find area using double integrals, but also there are ways to find volume using double integrals. So double integrals, you can find both area and volume using a double integral. And I'm going to start out by helping you guys recall that if I take the double integral of dA and there's no function in front of dA, that's the same as saying the double integral of 1 times dA. And honestly, guys, that is simply just going to be equal to the area of the region that you are integrating over itself. So if ever you're faced with an integral like this, where it's just the double integral of dA, all you have to do is look at the actual figure that they're having you integrate over and find the area of that. And many times this is just basic geometry. Essentially, you just end up getting the area over which you're integrating. However, if you take the double integral of a beach canopy of something, if there's a function of x and y in front of the dA, that's going to lead us to a volume, not an area. So I hope you see the difference. The second double integral right here has a beach canopy that's hovering over A, that's being it's integrated, whereas this first double integral doesn't have a beach canopy. It's just simply the double integral of dA is just simply equal to A. So this is a very important thing to point out, and the reason why I'm pointing this out is because this next example here is simply asking us to find the area, not the volume. So because it's simply asking us to find the area, we're going to utilize this first fact right here. You'll see just momentarily that we'll utilize that fact. Later on, you'll be asked to find the volume, and we're going to utilize a slightly different approach. Now, before I continue on here into this problem, I'm going to go ahead and show you guys how to graph this in your graphing calculator. So many of you use the TI-84, so I'm going to go ahead and use the same calculator here. And if you ever need to graph in polar form, you simply click Mode here. And then you scroll down here to Function, Parametric, Polar. And you go ahead and just click over to Polar, highlight that. Then click Second, Quit. And then you'll notice that I actually already went ahead and did this. Now, to really properly do this, I just basically solved for R. Let me go ahead and show that again in my PowerPoint here. I went ahead and solved by R. I solved for R. I just took the square root on both sides, which gives you plus or minus. And I'm just going to go ahead and take the positive version because you'll see, as in many polar functions, excuse me, you can actually graph the complete curve of the lemniscate in this case using just the positive version of R. So once again, I'm going to go ahead and show you here. I have just 2 square root of cosine of 2 theta. I just pulled out that square root of 4 is 2. And this is what the graph looks like. So just go ahead and click Graph here. Now you'll notice there's like some gaps in the middle. It's just because the calculator can't quite handle filling in those gaps. It's just a little bit too much detail for it to handle, but these all should be connected, just so you know. And look, it's very symmetrical, isn't it? It's very symmetrical. It has 2 loops that have exactly the same size. And if we go ahead and take a look at the table here, so if I click Second Table here, I went ahead and picked some values here that would work for me. Now, you might be wondering where are these decimals coming from, but if you kind of take a look, notice I get a value of 0 here at this crazy decimal, negative 0.7854. And then it gives me some actual real values. And then at 0.7854, I go back to 0, and then all of a sudden it's error, right? Well, this basically shows me that I'm getting actual values from 0 to 0 here, then it's an error. And just so you guys know, if I were to pick values just before this decimal, I would get error also, because you're getting imaginary numbers there. If I just were to keep going down, as you can see there, if I were to keep going down, down, notice here at this value, I get 0 again. Now this actually is the number 0. 6.3 e to the negative 7 is a super small number, very tiny. So essentially this is 0. It's just that the calculator couldn't handle the calculations, I guess. And the point I want to make is this, is that this decimal here, 0.7854, is a very special decimal. This decimal here is just simply the number pi over 4. And this decimal down here is the special number 3 pi over 4. But even more important than that, I'm going to go ahead and keep backing up here. As you saw earlier, I also had a 0 up here at the number negative 7.854. Sorry, 0.7854. That gave me 0 as well. Basically, from this 0 to this 0 represents this loop on the right-hand side. So I'll say it again. This negative 0.7854 up to this positive 0.7854 represents this right-hand side loop of the lemniscate, and it's symmetrical, right? So if I want to look for the area that's inside this lemniscate, why do the entire lemniscate when I can just go ahead and evaluate between negative pi over 4 up to positive pi over 4 and be done with it? And then simply multiply whatever I get from that times 2 to get the other loop of the lemniscate. Thus, my region of the lemniscate here is just exactly that. It's from negative pi over 4 to positive pi over 4. Are giving me my angles, okay? And I want to stay within the lemniscate, so I'm going to go from the origin out to the actual curve of the lemniscate itself. And as you can see here, it's again the same thing that I typed into my calculator by simply solving for r. And then multiplying it by 2 to consider both loops. Once again, keep in mind that I'm looking for the area of the region. So notice that I'm taking the double integral of dA, or in other words, the double integral of r dr d theta. And this, of course, ends up becoming a very simple integral. This is just power rule. It's just 1/2 r squared. The 1/2 cancels out with the 2 here, so I end up with just simply r squared. From 0 to 2 rad cosine 2 theta. Plug that in, you end up with 4 cosine 2 theta. Yet another very simple integral for us to integrate. And you should end up with an answer of 4 when it's all said and done. So as you can see with this example, it was very useful for me to go ahead and investigate a few things using my TI-84, which you'll be able to use actually in most likely for your next exam, unless I change some of the instructions. But and remember, you are not allowed to use a TI-89 or any kind of thing that is like an algebra system or anything like that, computer algebra system. So keep that in mind. I will be checking for those during the next exam. But notice how if you are able to use a TI-84, you can investigate before you proceed, and it makes your setup of your integral, of your double integral, much easier. Let's go ahead and try another one. And for this next one, I went ahead and just gave you the region right away, because as I read this description, I want to talk about the region. So we're going to go ahead and graph the smaller region bounded by the spiral r theta equals 1, and the circles r1, r equals 1, and r equals 3, and the polar axis. Now, there's a lot of information going on there, so let's go ahead and just break this up piece by piece. The spiral r theta equals 1 is this guy. So it starts off here. Now, this thing actually goes forever closer and closer and closer to the origin, but it just never actually touches the origin. So this spiral is impossible to touch the origin with. So we just kind of started here for simplicity. But as we grow in value, this thing gets bigger and bigger and bigger, and it spirals out, 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 out. But you'll notice that the arrow here is going in this direction because actually the bigger the r gets, the smaller the angle of theta is. But I'm not really too concerned about that. Now, obviously we should know the circles r equals 1 and r equals 3. We did a few examples like that earlier. Earlier we had circles r equals 2 and r equals 5 in the first quadrant. So we've actually have had experience with these. Notice that here I have a circular kind of curve here. If I were to continue this curve around the entire 4 quadrants, I would end up with a circle of radius 1. If I were to take this curve here and rotate this around all 4 quadrants, I'd end up with a circle of radius 3. But notice we're just cutting it off here. We're cutting it off here because we are also being bounded by the polar axis. Now the polar axis is actually going to be when theta is 0, or the positive x-axis. The polar axis is basically this here. It's this portion right here, just the positive x-axis, when not only when theta is equal to 0, but it's also only when theta is equal to 0 on the positive x-axis. And we're considering the smaller region because like I said before, these circles continue all the way around all 4 quadrants. So there's actually 2 regions that are bounded by these very same curves here. There's this region here, the smaller region bounded between the polar axis and the spiral itself, between 1 and 3. But there's also the other one. You'll notice you get like a donut-shaped figure all the way back around. That could be the larger region bounded by the same spiral and the polar axis. So we're going with the smaller region for now. So having said that, let's go ahead and get to it. So essentially our region is bounded by these two elements here, where this time, you'll notice this is kind of an interesting problem. This time it's different because in previous examples, theta was between two constants. But here you'll notice that theta is in between a constant and something that's a variable in terms of r. Whereas r is the variable that's actually between two constants. Because of that, as we integrate using polar coordinates, now again, we're trying to find the area, right? So it's going to be the double integral of dA, or in other words, the double integral of r dr d theta. In this case, I'm going to use r d theta dr, because in this case, we have to integrate with respect to theta first, because you'll notice again, theta is strictly between 0 and 1 over r. And how did we get that? Well, it's right here. Just simply solve for theta here, okay? And then after that, go ahead and take the integral with respect to r from 1 to 3. Once again, becoming a very simple integral for us. And I'm getting 2 is the answer. Now in the last two examples, these were examples of trying to find area. Once again, when you're trying to find area, it's the double integral of just dA. And in this case, with polar coordinates, dA is r dr d theta. But what if I was asked to find volume? Here, we're asked to find volume. And we're asked to find volume under this plane here, okay, but above this disk. So since we're asked to find volume, that's going to change things just a bit, and we'll get to that momentarily. But before I do that, remember, just like in section 15.2, I can basically ignore this plane right here that we're actually integrating under that has the z in it, and focus primarily on our shadow. So I'm going to go ahead and focus on this guy to start us off. That's going to be our boundary circle. That means we need to stay within that boundary. We can't go outside of it. So I'm going to go ahead and rewrite that. Now, in my opinion, it would be best to graph this so we can see what we're looking at. I would not recommend you try to graph the three-dimensional plane here. I just recommend you just simply stick with the shadow and graph this. Now, me personally, I would go ahead and bring the y term on the left side. I would complete the square. And notice here I end up with a circle of radius 1/2. That's centered at the point 0, 1/2. And hopefully this makes perfect sense to you. Once again, I went ahead and I completed the square, got to here, so I knew where it was centered about, giving me the circle. But once again, in the instructions, it's asking us to use polar coordinates. So there's a couple things I want to point out. Number one, we want to stay within this boundary circle. So I'm going to go ahead and do a simple swap. You notice how here I have an equal sign. Pretty simple, right? But that would mean I would be just staying strictly on the boundary of the circle. I don't want to be on the boundary. I want to be inside of it. So notice I'm going to go ahead and rewrite, or retype, I should say, the same equation, but now I'm going to replace the equal sign with a less than or equal to sign, because this would indicate that we are actually staying inside this region. That's where we want to be. Again, it's not a circle, it's a disk. Disk is basically a filled-in circle. But also keep in mind, they want us using polar coordinates. Now, you are welcome to integrate using a double integral, trying to find the volume with rectangular, but you'll see that converting this to polar might initially look more difficult, but eventually, after you simplify, it actually becomes quite easy. So by doing that, let's go ahead and replace x. Now, you should know this already. X gets replaced with r cosine theta according to the formulas. Y gets replaced with r sine theta. And then all we simply do here is we go ahead and square the r cosine theta. We square the quantity r sine theta minus 1/2 by expanding and foiling out. And then simply solve for r. So again, take this inequality here, and we're gonna solve for r. Okay. Okay. And we end up getting, very simply, after this crazy mess here, we end up just simply getting, as long as r is less than or equal to sine theta, then we know what our boundaries are. So basically, stating that x squared plus this quantity, y minus 1/2 quantity squared is less than 1/4 is the same exact thing as just simply saying r is less than or equal to sine of theta. Now, to me, this is a much simpler looking curve to deal with, especially with polar coordinates. So let's go ahead, and I think we're now ready to set up our integral. Now, this problem is different than the previous problems. The previous problems were simply asking for area. This problem is looking for volume. So we're basically going to set up the double integral. Now, before you panic, this does look pretty crazy. But before you panic, all this is saying is we're looking to integrate the double integral over this region, which is just simply that disk you saw from the previous slide. Remember, we're staying within the radius of 1/2. I know it says 1/4 here, but you take the square root, it's actually a radius of 1/2. So again, this is just a fancy way of saying that we are going to integrate our double integral over the disk. That's all this is saying. Please do not panic. Also, because we're looking at a volume here, how do we find the integrand? How did I get this 12 minus 6x minus 4y? Well, just like in section 15.2, you simply take whatever is hovering above the region, whatever is hovering in this case above the disk, and solve for z. So if I solve for z here by simply subtracting 6x and 4y, that becomes my integrand. So this is 12 minus 6x minus 4y. Again, I just simply solved for z up here. And by plugging this into my double integral, I essentially go from it being an area to a volume now. And now I think we're ready to set up the polar coordinates. Now, the polar coordinates are going to look kind of strange at first, but give me a chance to explain why they are set up the way they are. We'll start with the easy stuff. So again, please don't panic. So once again, we're looking for a volume here. And here's what I got. Now again, before you panic, let me explain exactly why I have this following expression up here. So let's start with the easy. Again, what are we going to replace x with? Well, we're going to replace x with r cosine theta. And that's what I have here. Now you might wonder, well, why does it say r squared cosine theta? You might already know why, but I'll get to it in a second. Y I replace with r sine theta. And again, here I have r sine theta, but with an extra factor of r with r squared. But then also notice, though, that this 12 becomes 12r. Now that was not a part of the plan when it came to the formula. So how did I get this extra factor of r, not just for the 12, but for each and every one of these terms inside this set of parentheses here? And the reason why is because, once again, remember, dA is not just dr d theta. dA is r dr d theta. So that extra factor of r got factored, multiplied into this expression. So that's why I have an extra factor of r in each one of these. In fact, if I were to factor out an r from each term, this would end up being r dr d theta, and then it would make probably more sense that this comes down as just as 12, this comes down as just as 6r cosine theta, this comes down as 4r sine theta. So now you know where I got these extra values of r from. Now, why did I write it like this? Because I think it's going to be more visually appealing when I do my next step, and that's finding the antiderivative. But before I do that, let me go ahead and explain what's going on here. Again, now please don't panic. This right here is just a fancy way of saying, hey, stay inside the disk. That's all this means. Now, what's the disk? Well, again, as you saw from the previous slide, I replaced x with r cosine theta, I replaced y with r sine theta, and then I went ahead and solved for r, and we got sine theta. And as long as I'm staying within the disk here, staying inside the circle of radius 1/2, that's the same as me staying inside of just simply sine theta when we change it as a polar function, meaning that I have a radius of 0 up to sine theta. Now we are talking about a full circle here, so this might not be that big of a deal. Maybe you understand this based off our previous slide. I'll go back a little bit. Whoops, went a little too far. Sorry about that. So again, you'll notice that saying that I'm within this disk here is the same as saying that I need to be within r has to be less than or equal to sine of theta. That still gives me this same circle. Now a circle to many students means 0 to 2 pi. So you might wonder, well, why does this say 0 to pi? Well, you'll find that in polar coordinates, especially if you play around with some numbers in your TI-84, if you're using the polar function sine of theta and you plug that into your calculator, you'll notice that it actually creates a full and complete circle if you simply go just from 0 to pi. It's in that nature of the function of pi itself. Or excuse me, the function sine theta itself. So you actually do not need to go beyond pi here in this case. You just simply go from 0 to pi. And also it probably makes sense too, because if you actually take a look at the previous picture, it's all within the first and second quadrant anyway, so it kind of makes sense that you're only going from 0 to 2 pi. In fact, sine of theta starts here at 0 with the value of sine of 0. And we all know that sine of pi is also 0. Basically, it makes a loop all the way around back to sine of pi. And then you can just stop there. So once again, let me reiterate. You're staying within the disk by going from 0 to sine. And you only need to do one revolution from 0 to pi, not 0 to 2 pi in this case. Integrating with respect to r first. So again, this time we're integrating with respect to r. It's pretty simple because all this simply is basic power rule. All these thetas are staying equivalent. Now you'll notice I skipped some steps though. So again, I would recommend that you go ahead and pause the video here. It's just simple power rule for each one of these. And then plug in your limits, just 0 to pi over sine of theta, excuse me. You can pretty much disregard the 0, 1. And try to get this same thing that I got here. Once you get the same thing I got here, let's continue. Now again, this should be maybe not quite easy. It's a little bit tedious, but you definitely learned how to integrate this thing term by term in Calculus 2. So please refer back to your Calculus 2 notes and try to get this. This is a pretty big expression, I know. But once you integrate it, you should get this. It's based on your Calculus 2 notes, which ultimately gives you 5 pi over 2. Now the funny thing about this is that to integrate this, you actually did not need to use double integrals at all. You could have done this geometrically. But because we are learning how to integrate this using polar coordinates, I won't at this time show you how to do this geometrically, at least not right now. But if you already understand what I'm saying, you can confirm your answers using a little bit of geometry and formulas from geometry to confirm the result as 5 pi over 2. This is a great problem for you guys to do from beginning to end because, again, it shows you how to convert from rectangular to polar in a pretty clever way. And then it basically gives you a lot of review from Calculus 2, especially with trigonometric functions. So I would highly recommend that you do this problem from beginning to end on your own at some point. Maybe maybe I would say do it later today if you can, now that you kind of have a general idea of it, and then try to do it by yourself without looking at the answer here. Let's go ahead and do one more example. Let's try to find, once again, the volume, not the area, but the volume of a sphere with radius A. Now, before I try to set up the integral, let's go ahead and remind ourselves what is the equation of a sphere, in this case with radius A, and we presume that it's going to be centered at the origin. I think all of us would know that this would be the equation of a sphere. And you know what, I'm just going to go right into it and give you the integration that I would get to find the volume of a sphere with radius A. It would look something like this. Once again, before you panic, let me go ahead and break this down for you. Since we are finding volume, we are once again going to take this equation here and we're going to solve for z. Now, if you solve for z, you end up getting plus or minus the square root. We're going to go ahead and just take the positive version of that. And then on the outside here, I'm going to multiply by 2 because we all know that above the z-plane is the positive version of the sphere, and below the z-plane is the negative version of the sphere. But if you take the negative version of the sphere, you're going to cancel out that volume with this volume. So instead what you do is you simply just stick with the positive sphere here, that's this guy, and just multiply it by 2 to get the entire volume of the sphere. Now you might be wondering, well, what's this all about? Well, this here is actually the projection or the shadow that is being cast onto the z-plane, onto the floor, which is just simply a circle of radius A. So in a very real sense, it's similar to the last problem. The only difference is that the last problem was not centered at the origin. This one is. And this is just simply a circle centered at the origin of radius A. And now we go ahead and convert to polar coordinates, looking like this. Now this time, our radius is from 0 to A, based on our disk here. And this time also, we are going to go ahead and go from 0 to 2 pi, because this time we are actually going to go all around the entire origin, all the way from beginning to end. And then once again, you just simply replace, I'm going to factor negative out of here. I get x squared plus y squared. That's how I got the negative r squared here. And again, dA is replaced by r dr d theta. Now what's nice about this particular problem is that a is a constant here. So I actually can integrate with respect to r first or with theta first. It doesn't really matter. In fact, these are separable as well because you're talking about an expression that is explicitly in terms of r multiplied by an expression that is explicitly in terms of theta. So this is also separable. And so pretty much you can integrate this however you wish. I'm going to go ahead and give you what I have. And again, I would advise you to pause the video here and try to integrate this yourself. I want to first point out, though, that if you take a look here, you'll notice here I have this limit from 0 to 2 pi with this d theta over here. Well, remember, that's just the area of the region that you're integrating. So these two here together just end up becoming 2 pi. And then 2 pi times 2 pi is simply 4 pi. So that's how I get the 4 pi down here. 2 pi times this 2 is 4 pi. And this over 3 business here is based off of you doing just basic U substitution from Calculus 1 to solve this portion. So once again, this is a very good integral for you guys to practice on your own, especially if it's been a while since you've taken Calc 1 or Calc 2. It'd be in your best interest to pause the video now and try to get to this antiderivative, before you continue. But then finally, we go ahead and finish this off by using the fundamental theorem of calculus part 1. And you'll notice we get 4 pi over 3a cubed. And the funny thing about this one is that I did not need to use a double integral at all to get the answer. If you recall, what is the volume of a sphere from back in your basic geometry class? The answer is what? It's 4/3 pi r squared. In this case, r is a radius of a. So here, 4/3 pi r cubed, I should say. In this case, I have 4/3 pi a cubed, because again, that's the radius in this case is a. But if you're thinking, well, why didn't you just tell me that in the first place? Well, why do you think, or how do you think they actually got the volume of a sphere in the first place? They got it using this, among other methods, but this is one of the methods how they proved that the volume of a sphere was, in fact, 4/3 pi r cubed. Well, this concludes section 15.3. Please let me know again if you have any questions. Please timestamp wherever you have any questions and email me your questions as soon as you can, especially before the homework is due. Have a good day, and I'll see you next time.